Welcome to Homework Lib.
Hi, so for the first two sections, I'm going to write down like the general equation of dissociation of the acid. I'm going to use a simplified notation without the hydrogen ion. So essentially what we're going to have in both of the cases, if we do a nice table, we have C0, the amount of change is going to be minus X, that is the amount that dissociates. So we end up with C0 minus X, and X. Okay? With this, our Ka becomes x squared divided by C0 minus x. And now, for both of the cases, what we are going to be able to do is that if C0 is much larger than x, then C0 minus x is approximately equal to C0. What is the condition for that? That our final result, x, needs to be lower or equal than 5% of C0 for that approximation to be valid. So let's do it with both of the cases. In the case that that approximation is not valid, you need to solve the full quadratic expression coming from this. So first let's look at HClO. The Ka is going to be 2.9 times 10 to the minus 8. The initial concentration is 0.082. So my Ka becomes x squared divided by C0. Okay? Solving for x, which is equal to the concentration of H plus of this monoprotic acid, what we're going to get is 4.87 times 10 to the minus, actually 88 times 10 to the minus 5 molar. Recall that this equation implies that x is equal to the square root of Ka times C0. Okay? With this, the pH, which is minus the logarithm of that concentration, the result becomes a pH of 4.3. So that would be the pH for the first solution that we have. For the second one, we have something very similar, but now the thing changes. Now we have a base, that is going to have an initial concentration of 0.448 molar. The base, I'm going to label the base as B minus, and the associated acid, Hb, has a Ka equal to 5.4 times 10 to the minus 10. That means that the production of Hb, it is going to be the inverse of Ka, so it's something in the range of 10 to the 10, which we can assume safely that it is going to be a very quantitative solution. That means that almost all of the B minus, all of the H2BO3 minus that we have, it is going to turn into H3BO3 in a very quantitative way. So we can follow the same procedure, and the ice table, it is going to look the same, and C0, it is going to be again 0.448. So now, since we already solved this thing, the K is going to be again x squared C0 minus x. So x is going to be, with our approximation, C0 times Ka. And Ka is this value. So the result that we're going to get is 1.55 times 10 to the minus 5. Remember that this is going to be equal to the concentration of H2O plus or of H plus that we have in solution, right? So that implies a pH of 4.808. Okay, so those are the first two solutions that we have. Now, next up, what we're going to get is essentially something that behaves as a buffer. Okay, so we have different compounds, NaH2PO4. This one dissociates into sodium plus H2PO4 minus. The other compound that we're going to have in solution is Na2HPO4, which dissociates into 2 Na plus HPO4 2 minus. And finally, we're going to have KOH, which dissociates into K plus OH minus. And the concentrations that we're going to have in the beginning, it's going to be respectively 0.3 molar. From this one is going to be 0.84 molar. And from the last one, it is going to be 0.054. So for this case, what we are going to deal with is, since we are adding a base, what is going to happen is that the strongest acids in solution is going to react, this weak acid is going to react with HPO4. Okay, so we are going to have H2PO4 minus plus OH minus, and this is going to generate HPO4 2 minus. Okay, we can realize this directly, that OH minus is going to be the limiting reagent because that's the one that we have in the smallest proportion. So let's draw our ice table. H2PO4, we begin with 0.3 molar. All of the quantities here are going to be in molarity. OH minus, we start with 0.054. And HPO4 2 minus, we begin with 0.84 molar. The amount of change, it is going to be essentially the concentration of OH minus that we added. And over here, 0.054. Okay. That means that at equilibrium, we just need to add up everything here. We're going to have 0.246 molar, something close to zero. Again, all of this in molarity. And HPO4 2 minus, we are going to have 0.894 molar. So in this case, what we have is the combination of an acid with its conjugate base. Which is a buffer. So now the pH, it is going to be equal to the pKa for this pair. Here you need to be careful. If you look the pKa's for phosphoric acid, you're going to find three different values. The first one is for H3PO4 going into H2PO4. The second one for H2PO4 towards HPO4. That's the one that we want to use. And the final one is HPO4 going into PO4 3 minus. Okay. So we need to find the pKa of HPO4, H2PO4. So the value for that one is going to be equal to 7.2. So the pKa for this one is 7.2. Okay. And for getting the pH, we need to use the Henderson-Hasselbalch equation that tells us that this is equal to the concentration of the conjugate base divided by the concentration of the acid. As I said, this is going to be 7.2 plus logarithm of conjugate base, which is 0.894, divided by the conjugate acid, 0.246. Using this equation, our final result of pH is going to be 7.76. Cool. And with this, we can follow up with the last one, that is a titration of a phenol with OH minus. So we start with a phenol, C6H5OH plus OH minus. This is going to produce the phenolate plus water. Okay. So in order to get this result, first of all, we need to calculate the concentrations. So at the beginning, the amount of mole that I have, and actually we can stick it with just doing the ice table in moles instead of molarity. In this case, you're going to see in a minute why. So the initial amount of mole that we have of the phenol is going to be 15 milliliters. Convert that to liters and multiply it by the concentration of the phenol that we have. I'm going to abbreviate it as phenol, which in this case is 0.1 molar. And with this, we're going to get a result of 1.5 times 10 to the minus 3 mole of phenol. And we need to compare that with the amount of NaOH that we added. The same procedure, but now we need the volume added of NaOH. And this, in this case, the concentration is 0.15 molar. So the result is 9 times 10 to the minus 4 mole of OH minus. For both of these quantities, we could do the calculation of the concentration by dividing this by the final volume. In this case, the final volume, it is going to be equal to 21 milliliters, which is 2.1 times 10 to the minus 2 liters. Okay, so you can do that division, or we can go directly with the ice table and using the amount of mole. So the amount of mole that we have at the beginning of phenol is 1.5 times 10 to the minus 3. That reacts with 9 times 10 to the minus 4 mole of OH minus. The amount of change is 9 times 10 to the minus 4 because OH minus is the limiting reagent. And that is going to be the same amount of the phenolate that is going to be generated. So at equilibrium, we're going to have 0.6 times 10 to the minus 3. We're going to have something close to 0, and we're going to have 9 times 10 to the minus 4. Mole and mole. Now you are going to realize that again we have an acid with a conjugate base. So we are going to have again a buffer. But the nice thing about buffers is that I'm going to erase the calculation that we did here. The nice thing about buffers, and about using, in this case, the amount of mole, we don't need to calculate the concentrations again, because if we do concentration of the phenolate of C6H5O minus divided by concentration of C6H5OH, this is going to be equal to N base divided by final volume divided by N associated acid divided by final volume. Final volumes cancel, and we get N of C6H5O minus divided by N of C6H5OH. And this is one of the few cases when we can do it directly, okay? Just by using the amount of mole. So again, we're going to use the Henderson-Hasselbalch equation. pH is pKa plus logarithm the coefficient of those concentrations. We need this value here, but now this is 9 times 10 to the minus 4 divided by 0.6 times 10 to the minus 3, or divided by 6 times 10 to the minus 4 directly, right? This is going to depend on the value of the pKa of the phenol by looking that value online, because it's not given in the problems, or you can look it on tables. The value for the pKa is 9.98 plus logarithm of 3, essentially. The result, sorry, not logarithm of 3, logarithm of 9 over 6. Logarithm of 1.5. So this is going to give us a final value for pH of 10.156. And that is the answer for the last one.